quick announcement. I forgot to say this after the last exam. Just for what it's worth, do what you want. You're all adults. But I've seen some sample questions from the material that get filtered through Quizlet, and they suck. So please be forewarned before you start running material to start generating questions for the class. Just be aware, I've seen some questions that really adulterate the material and they come out asking things that really don't make sense or they answer them incorrectly. So do what you will, but just I wanted to warn everybody on that one. Quiz next week, I guess. So there's a practice opens today. Quiz will be coming on Tuesday, just for what it's worth. I think that's it for announcements. Does anybody have anything before we dive in to today? All right, so caffeine will be the main thing with some overlap with energy drinks and then polydrug with alcohol. But caffeine itself is what we're going to focus on, and we won't do a historical one. Yeah, there's so many different sources of caffeine, but it should suffice to say that this is the most widely used psychoactive drug in the world, with an estimation that about 90% of adults in the world consume some kind of caffeine every day. I guess, yeah, to cut right to the chase, caffeine is an adenosine receptor antagonist. We'll get into that in a little bit. And average daily consumption is 250 to 350 mgs per day in the US. And that's got to be, well, I wonder how big that sample size was. I got to imagine universities consume a lot more than, I don't know, other areas. But anyways, here's a picture of caffeine, or this is what the molecule looks like. And here's adenosine, so you can see very similar ring structure. Some of the spinach off the side is different, obviously, but it makes sense that caffeine will work at adenosine receptors if the receptor is usually accepting this molecule. So, but caffeine, yeah, this is, I don't know, the most obvious couple slides, I guess. Sources of caffeine. Everybody's familiar with tea and soda and energy drinks. I should probably update this. This was about the original one there. But some, I guess, non-standard chocolate. I'm sure most people know chocolate contains some caffeine. I love the energy mints that have caffeine. No-dos, these are big during finals time. This one I love. If you can't find a way to get caffeine into your body, you can always buy soap. And just take a shower, and you get 200 mgs per shower with caffeinated soap. So that's hilarious, but anyways, lots of different sources for this drug. But what it does, so moderate doses of caffeine can have positive effects: increase alertness, enhance memory, fine motor coordination, increase motor activity, and increase your mood. Put a smile on that face, everybody. Definitely those that need that cup of coffee in the morning do it, but more specifically, it works through adenosine receptors, right? Adenosine receptors, either A1 or A2A, both of which are GPCRs, and we'll cover their specifics in a bit. But this is what's really interesting about this system, that they have two different receptors in our body, same receptors that accept the same ligand, that have two completely different physiologic responses, right? So A1 adenosine receptor is the wake promoting receptor, all right? So the endogenous ligand adenosine, if it's bound to this receptor, you'll have low activity. So low activity in the wake promoting sense. But if you have caffeine there, you have high activity, so it's going to stimulate wake-promoting activities. Opposite for adenosine receptor A2A, this is the sleep-promoting. So the adenosine in your body, the endogenous ligand, will have high activity there, so it will promote sleep, whereas caffeine will not, right? Caffeine helps you wake up. So it's going to have low activity on the sleep-promoting style adenosine receptor, high activity on the wake-promoting receptor right. And I did want to say, I forgot, I apologize before I started. I made a change right before class with a couple slides, so if you downloaded them before 15 minutes ago, there's a slight change. It really doesn't affect a lot. I didn't like a certain slide, so I tried to cut it into two. Hopefully it's more straightforward, but anyways, back to character. So this is a really interesting system, right? Because you have two different receptors within the same family. They have two opposite effects. And yeah, we'll walk through a little bit more of that in just a bit. But this also is used, caffeine is also used to treat migraines or for weight loss, right? Yeah, migraines, headaches, and weight loss. So with, I guess, some efficacy there, depends on the individual. But moderate doses of caffeine can cause negative effects. So this really depends on the individual, you know, and it definitely is more in terms of tolerance. Some people start drinking coffee when they're 8, so by the time they're 21, they're drinking 2-3 pots a day, and they don't have so many effects. But those who are, you know, caffeine naive most of their life, and then they come to college, they have a much more profound effect. But the negative effects can be if it works as a diuretic to help shed water from the system, right? Or it will prevent your normal sleep cycles and cause sleeplessness in people, can trigger anxiety and headaches, and then also there's a cardiac effect. Overall will increase heart rate and blood pressure, but it's usually a more milder effect with some of those. However, this is the thing about this drug, it has kind of a wide range of things that it does. Even though it's on the milder side of the scope in terms of stimulant drugs, it does have a wide range of effects, okay? So, one of the biggest things about caffeine is its absorption. For the most part, in adults, it'll be completely absorbed within 45 minutes. And this is, as a structure, you can see this is a fairly lipophilic molecule, so it gets all over the place. It can get into the brain, but it can also get across placental barrier, and this is where you can have a lot of trouble with this drug. Due to the fact that the metabolism of this drug has a wide range of time, or half-lives. So as we said, 45 minutes, right? So for adults, it's very short. During pregnancy, this metabolism kind of lacks, and it's more about absorption and some slight decrease in metabolism. But here's where the big problem happens. It sticks around forever in babies, and yeah, whether they're inside or outside of the womb, it sticks around forever, for a long, long time with them, and this is where you can have problems. Okay, we'll get into that in a bit, but in terms of metabolism, this is broken down by cytochrome P450, CYP1A2, all right? So we've got caffeine here, and several different metabolites. Paraxanthine is the most common metabolite of caffeine, and this works similarly to the parent compound, right? So it's just as potent as caffeine. Theobromine, this is a caffeine-like substance found in chocolate, so a similar effect. It's not as potent as the other two, but it still does have some activity at adenosine receptors. Theophylline is really interesting. So this is the smallest amount of metabolite from this drug, but it branches into kind of new clinical applications, if you were. It is more potent than caffeine, but it also works as a bronchodilator that can be used with asthma and respiratory distress. Also been used as a performance-enhancing drug, if you will. Theophylline is not a great drug, real narrow therapeutic index, but I knew, athletes from days of old that used to pop a theophylline pill before they go on a bike race or in a race or whatever. It can help their breathing a lot, so athletes used to dose on this before getting into competition, but it's really fallen away. I don't know if people even prescribe it anymore. But CYP1A2 breaks this down. 3 different metabolites are important here, and why they're important is stated there. So, all right. So, in terms, or getting back to that, the problem that happens with caffeine, especially with newborns or in utero babies, as this shows, this is a meta-analysis that looked at caffeine use and low birth weight risk. Okay, so here is a list of all of the different studies. They have them broken into low, moderate, and high caffeine intake. The results are shown on this kind of unfortunate plotting here, but the bottom line here is, so they looked at daily caffeine use, split it into 3 different tranches, if you will, or 3 different cohorts in terms of how many milligrams of caffeine they would take on a day. Low would be 50 to 150-ish mgs, moderate 150 to 350, above 350 milligrams a day is considered high daily caffeine intake. Yeah, statistics are good on all these studies, but this is striking. So 13% low birth weight risk per 100 milligrams of caffeine consumed. 100 milligrams of caffeine, that's a cup of coffee. That's not much at all. So having that per day, each 100 mgs that you consume, you increase the low birth weight risk by 13%. Even more striking, almost 10% or 7% higher risk of pregnancy loss with every 100 mgs of caffeine a day. So every cup of coffee, taking a chance of losing a child. So very striking. I shouldn't make light of that or make jokes, but yes. So this is a very striking finding, but fairly well representative in terms of the veracity of data, if you will. So also interesting to note, there's a biphasic effect of caffeine at the lower doses, right? So 5 to 20 micromolar, 1 to 2 cups of coffee a day, you get the CNS stimulation that we're talking about. One up from there, 50 to 200 micromolar, or 10 to 20 cups. Now we're getting pretty unrealistic. You get CNS depression, and we'll get into the molecular aspects of that. But then after that, if you get above 80 cups, if you can drink 80 cups, you get more. So you have stimulation, then you have depression, then you have further stimulation is the bottom line here. 80 plus cups can lead to convulsions and death. I don't know. Again, yeah. Being able to drink 80 cups of water would be impressive, let alone coffee. But biphasic effects of caffeine work like that. So sort of tying a little bit of big picture stuff together. So we've talked a lot about cyclic AMP in terms of the product from G proteins when activating a GPCR. Adenylyl cyclase will convert ATP into cyclic AMP. Cyclic AMP gets broken down by cyclic AMP phosphodiesterase, which is blocked by caffeine, theobromine, and theophylline. Okay, this enzyme will create a adenosine monophosphate, if you will, and then just plain adenosine is shown here. But the cyclic AMP is important for increased heart rate, smooth muscle relaxation, and then inhibition of vasopressin, also known as antidiuretic hormone or ADH. That's where that diuretic effect of caffeine comes in, because it inhibits vasopressin. That is the standard antidiuretic in our system. That really controls how much water loss we go through on a daily basis. But so here we see multiple effects of caffeine in terms of their concentration. Yeah, so in order of potency, you can see here. So dose response curve, we've got caffeine concentration in molar units on the bottom, and then as plotted as the effect of it is plotted as a function of concentration. As you can see in the lowest concentration, this is where it works as the adenosine antagonist, right? So at these concentrations, so they're saying roughly 20 micromolar, this would be Usual concentration for just an average coffee or tea drinker per day, where you're going to have the wake promoting effects of this drug, right? Stepping up from here, you can see above this range, or the toxic doses here, you have the phosphodiesterase inhibitor that we just looked at. Even higher amounts will cause a release of intracellular calcium store and then blockage of GABA receptors. And all of these are going to be in that toxic phase of well above, 300 micromolar. So anyways, these three more toxic effects, these are kind of the standard or clinical or desired effects of caffeine, but it's good to know those four. You don't have to know the specific concentrations, just that they have these different effects. Okay, so a bit more of the specifics here, and we'll get into this in better looking slides in a minute, but adenosine A1, A2A, here's our receptors. A1 is coupled to G-alpha I, GIO here, but for an exam, just say GI. And as we've seen before, this can stimulate potassium channels and inhibit calcium channels, right? So this will overall effect will decrease the neuronal excitability with adenosine, all right? Adenosine A2A receptor is coupled to G-alpha S, so that's going to stimulate adenylate cyclase, causing a production of cyclic AMP, and you'll have increased neuronal excitability with the endogenous adenosine bound. So going into the specific receptors themselves, A1 is the most abundantly expressed adenosine receptor within the brain. Highest levels of expression in the hippocampus, cortex, and cerebellum. Boom, all out here. A1 receptors will inhibit neuronal activity. Okay, so a better look at about how this will, the effect of caffeine here. So on the left is the endogenous sort of effect within our body with no stimulation. On the right is the effect with caffeine. So the blue circle here is a glutamate interneuron, okay, within the cortex. And what we're looking at here is the effect on cognition, okay? We're within the cerebral cortex. The effect of caffeine on cognition will be something like this. So we've got a glutamate neuron synapsing on a glutamate neuron within the cortex. So glutamate is released, binds to a glutamate receptor, causes an increase of adenylate cyclase activity, with adenosine bound to the A1 receptor on this glutamate neuron. It's going to inhibit adenylate cyclase activity. So the overall aggregate is going to be a moderate amount of cyclic AMP activity. You get moderate glutamatergic outputs. This will cause a modest attention or cognition in this space, okay? That's standard kind of flow, if you will. Now with caffeine on board, so same setup, right? We've got glutamate neuron, another glutamate neuron, glutamate's released, binds to its receptor, causes adenylate cyclase to be active. But now with caffeine on board as an antagonist, it's going to shut off A1, so we have no input into the adenylate cyclase activity. So we get only the input from the glutamate neuron, high levels of cyclic AMP, increased glutamatergic output, and enhanced attention and cognition, okay? So caffeine, an antagonizing adenosine A1 receptor, is going to allow for increased amounts of cyclic AMP in this glutamate neuron within the cerebral cortex. That's going to enhance the attention and cognition within this person or within this animal. All right, and you can show that through fMRI studies. As you see here, we've got these 5 different brains that are being scanned. And they'll be scanned after caffeine treatment or placebo. I don't know what that is for this, but the idea is you can see here, the more orange and red you can see, the more cerebral activity we see. So comparing all 5 of these panels to the placebo panels, we can see in each instance, there's a lot more activity going on there, translating to the enhanced activity in the brain due to caffeine's effect, right? So on the other side of things, the A2A receptors will be involved in motor control, and we're talking mostly within the nigrostriatal dopamine system. We've learned before. So this plays an important role in the neurotransmission of dopamine in these areas, as we'll look at in just a minute. A2A highly expressed in GABAergic neurons in the striatum, which will control the motor behavior or motor control, right? As a quick aside, these are the neurons that die off in the development of Parkinson's disease. Excuse me. So we know Parkinson's disease heavily involved in dopaminergic transmission, but these are the specific neurons in the nigrostriatum that will die off during development of Parkinson's. Okay. So for this instance, same setup as we just looked at. We're talking nigrostriatal system, we're talking motor control, we're talking A2A, all right? So this time we've got a dopaminergic input onto a striatal GABAergic interneuron. So the blue circle is now a GABA neuron. We've got D2 receptor. Dopamine is going to be binding to D2. D2 is coupled with G-alpha-I. It's going to block adenylyl cyclase. Adenosine binding to A2A, which is coupled to G-alpha-S, is going to stimulate adenylate cyclase, which aggregate again, moderate levels of cyclic AMP, so you get a moderate GABAergic output to the motor control, and then a controlled decrease of motor activity. Yeah, don't worry about, this is essentially supposed to be saying this. Okay, you know, the T is usually an inhibitory thing. In this instance, this inhibitory thing is a controlled decrease in motor activity. Not that it's going to inhibit a controlled decrease, okay? Just so that's clear. I know this, yeah, still working on this figure. Now, going to the other side with caffeine on board. Same setup, dopamine coming out, binding D2. G-alpha-I, so it's blocking adenylate cyclase activity. Caffeine binds to A2A. No input there. Decreased cyclic AMP, decreased GABAergic output to motor cortex, so an increased motor activity overall. Okay? How does that sound, everybody? So this is, I don't know, if you're bored or looking for something to do and you can't find something to do on the internet, look up drug studies with spiders. It's amazing. There's several times these studies have been done. This is only one. So as you can see here, there's a spider web that's done with a drug naive. The spider didn't get anything, and this looks like a normal spider web, right? Give that spider some caffeine and look at the dumpster fire that their web turns into. But if you go look this up, the webs that are made on marijuana, the web that they make on LSD, you've got to check that out. Even before we get into hallucinogens. It's amazing. Anyway, so that's kind of interesting, I think. But yeah, something to check out if you're interested in that. But yeah, that looks horrible in terms of how that affected that poor spider's web. Yeah. So there's that. Okay. As far as control goes, how does this sound, everybody? That's the big one for caffeine. Remembering that it hits A1 and A2A, and then that there's an opposite effect depending on if you have adenosine or caffeine bound. Good? Good. Okay. So again, this is the pathway that's affected in Parkinson's disease, and there's studies that have shown that caffeine intake can lower the risk of developing Parkinson's disease. Specifically, men who do not drink coffee were 5 times more likely to develop Parkinson's disease than those who drink more than 28 ounces each day. Take that with a grain of salt. I don't know how many confounding factors there were in there, but that, yes, the connection between daily caffeine consumption, regardless of if it's coffee or not, and a decrease in Parkinson's development is fairly well represented in the literature, but again, an exact causal, a real direct cause between the two phenomena hasn't really been established. But, so, A2A adenosine receptor antagonists can reduce motor deficits in animal models of Parkinson's disease. And there is a thought that this could reduce inflammation or oxidative stress. So don't worry about that for the, anything important, because that's pretty controversial and shouldn't really be taken hold. So, as far as categorizing this drug, the DSM-5 lists caffeine use disorder, but stops short of declaring it an actual addiction. And it's kind of interesting because if you read through what they say about the use disorder, it really sounds like something very similar, right? Repeated but unsuccessful effort to quit back or quit using it, continuing to use even if there are adverse effects while using it, needing more and more of it to achieve wanted results, and then using this drug in order to relieve or avoid withdrawal symptoms. All point towards addiction as I've studied it, but it is still just a use disorder technically, so take that, again, another grain of salt. So approximately, almost 10% of the general population has caffeine use disorder, and then there are specific genetic associations with this disorder. Polymorphisms in A2A receptor gene have been associated with this use disorder, and then variations of CYP1A2 have been shown to, associated with increased caffeine consumption, and then those with low expression have shown increased risk for cardiovascular toxicity, just simply because you can't clear it out fast enough. And the more negative effects have a larger chance of presenting themselves. All right, so starting to muddy the water here, talking about caffeine in terms of energy drinks and their effect with alcohol. So when talking about well-being, looking at the effect of energy drink or caffeine, alcohol, and then the two together. And so people were questioned, what is your well-being on a score of 1 to 10, 1 being the worst, 10 being the best that you've ever had. Most people said, I'm doing okay. Whether, so before they had anything will be in white, and then the darkened in bars will be 30 minutes after ingestion. In terms of taking an energy drink, their well-being stayed the same. I'm fine. Half hour later, I'm still fine. In terms of booze, they're fine, and then a half hour later, they're great. They're doing real good. But compound this with an energy drink, and they're over the moon. So the energy drink can potentiate the effect of alcohol. But interestingly enough, we'll get back to what's interestingly enough. So quick aside here, Four Loko, this is, a carryover slide, because I just love to make fun of those Buckeyes. So apparently this was developed down at that school in Columbus, isn't it? Something like that. But it's alcohol, and they mixed in caffeine and a bunch of metabolites and some fruity flavors and a ton of sugar. And then they just put it out on the market, and then they just left. So sure enough, what happened though is they had a bunch of parties where students were hospitalized for this, and it only took 5 years for the FDA to come back and cracked out on them. And in kind of a comical response to that, so the FDA said, you can't have alcohol in with all this other stuff because these people will drink it up. They get all ramped up on caffeine, then they get all wasted on booze. They think they're doing great, and they do all these ridiculous things, and then they're all in the hospital, so you can't do it. So instead of removing the alcohol, though, they took out all the other stuff, which is kind of clever on their part, because it was the caffeine and the metabolites that are masking the effects of alcohol, okay? And that, yes, is one of the biggest problems with mixing caffeine and alcohol, is that you can feel the excitement from the alcohol, you can feel the sort of revival from the caffeine, but you still have the inebriation from the alcohol, and it doesn't change. And that's one of the biggest common misconceptions when people mix these two together, is that they can drink more alcohol if they have energy drinks or high levels of caffeine on board, and it's just not true. You're just as toasted on the alcohol, but you just are up more. You're not more coordinated and you're not more aware, but you think you are. And anyways, in terms of how energy drinks or caffeine can affect alcohol pharmacokinetics, it doesn't, right? If you look at blood alcohol level and you give 2 different doses of alcohol, either 0.6 grams per kilogram or 1 gram per kilogram of alcohol, and then you have an equal cohort that you give an energy drink to along with that dose of alcohol, you can see that the concentration of alcohol in the blood well out to 2.5 hours remains essentially the same, right? So these people might be a little bit more up, but they're not breaking down the alcohol any better, and they're just as inebriated as those without the caffeine on board. And even though you're a bit more up or alert, you're not more coordinated or you're not really more alert, you just feel more awake. So as this study shows, they're looking at 4 different cohorts, control, energy drink, and then alcohol plus energy drink. And you can see they have the baseline here that they're all essentially the same, so they're looking at reaction time in some. But all 4 cohorts essentially have the same type of reaction time. Then half hour after they drink, we see a delayed reaction time in both cohorts that had alcohol, meaning they were slowed down with the ethanol. But we see the same reaction time in the alcohol plus energy drink as the alcohol. And then the same thing out to 2 hours, where they're all overlapping now, so it's not that great a division. But the bottom line is, it doesn't improve reaction time, even though you may feel a little bit more awake or alert. And this is the one that I cut up here. So, yes. In terms of believing that the caffeine will have an effect on how you behave when you have ethanol on board, this study shows how expectancy can have an effect on your behavior, but it's kind of in a negative direction. So what they did, this study shows, they had a computer game, right? And in the computer game, they gave someone a mouse with a cursor that they had a moving target that was cruising around. They had to keep the cursor on a moving target. I should have put a moving target on here, but everybody understands what that looks like. So what they did is they gave them alcohol and caffeine, and they told one group that the caffeine would counteract the effects of the alcohol. Then they told a second group that it would not. And interestingly enough, the expectation that caffeine would reverse the alcohol impairment led to a decrease in motor performance, as you see here. So the dashed line is the performance of the no counteraction. The solid line is the activity of the group that was told it would counteract. So as you see here, the 0 level is the drug-free baseline of reaction time. So if you go above that, you're reacting better. If you go below it, you're reacting worse or longer time. And the entire performance of the group that was told that caffeine would counteract the effects of alcohol performed worse than those that were told there is no difference there. So it's the suggestion that people bought into that they should be able to do better on a test when they have caffeine and alcohol actually caused them to perform worse. They were expecting this benefit and it actually doesn't have an effect at all. Doesn't have a beneficial effect. And that leads to situational specificity type tolerance. So this is a learned tolerance and it applies to most all drugs really. Drug use in a familiar context produces tolerance, okay? So if you drink 6 beers, well, we'll just use the example that's plotted here. So if you do heroin in a familiar environment, the effect of the heroin will be decreased because you're used to being in the environment, right? So you develop a certain amount of tolerance, and then due to that, you think that you need more, or you will need more, because you have developed this learned tolerance in a familiar environment, all right? So the idea though is that because you don't get as big of a boost from the heroin, you take a higher dose and you get used to that higher dose in your familiar environment. The problem happens when you leave your familiar environment and you go to a new environment, but you're used to a higher dose of heroin that might be borderline toxic, and you don't have that tolerance there. And then it has a much bigger bang on your system than it usually does, and this is what can lead to lethal consequences. Due to the fact that you're out of your environment and you're not used to where you are. Your body will still process this heroin, however, the way that your brain responds to it will be different if you're in an unfamiliar environment versus a familiar environment. And this is what can cause problems in people who, develop a certain tolerance in a very safe environment. And if they rarely leave that environment, they get used to dosing at a certain level. If they leave that environment though, they don't have that same tolerance, and then this is where problems can arise. So, situational specificity in terms of drug tolerance. Okay. There has been shown to be increased risk taking with people who are heavy energy drink users. As this study shows here, now this isn't a huge take-home message, and again, some confounding factors, but they took all of these energy drink users and, they took all of these people and they split them up into those who use energy drinks and those who don't. And as you can see here, then they question them in terms of their inebriant use every day, and then if they use cigarettes or pot or ecstasy. And without going through the numbers that much, there's a lot more usage in all of these in the yes, I am an energy drink user cohort versus the no, I do not use energy drinks. So there's a correlative there. And that was the last one. So, multiple benefits of caffeine. Some are good, some are bad. All depends on the dose, as usual. Moderate amounts of caffeine can improve cognition and motor performance, but caffeine can also mask intoxication, so it doesn't take away intoxication, it just makes you think that you're less intoxicated. And then this can promote behaviors that aren't so great, but summary, but have a good one, everybody. See you Thursday.